Hello everyone, welcome to Lecture 7 Part 3. Here we're going to be talking about cognitive task analysis and a type of task analysis called GOMS. Okay, so this part of the lecture is going to be a little bit shorter, but not too short, but we've already gone gone over a lot of task analysis. So the cognitive task analysis is a little bit different. It still informs the design process, but it does so through application of cognitive theories. Some task actions are cognitive and not behavioral. They happen in our minds. They don't really happen somewhere where we can see them. So the hierarchical task analysis often focuses on actions. The cognitive task analysis focuses on other things, including perception and cognition. So here are some examples. Deciding which button to press. This is part of the task, but it's not described in a formal HTA. Recall previously stored information from memory. So this is also not included in a regular task analysis. Comparing two objects, yet something else that's part of a task but not captured by a traditional HTA. So the CTA follows a processor model. This model is an internal representation of processing that occurs for the purposes of designing a task that can be undertaken more effectively by humans. Okay, so we have the cognitive, perceptual, and the motor, and all of that to make up the model of this processor model. So this is what we call the model human processor. That image that I just showed you is what we refer to as the model human processor, the cognitive, perceptual, and motor. It's the framework that integrated literature on cognition and human performance. So cognitive task analysis doesn't just look at the task; it looks at human performance from a cognitive perspective. It talks about those three main processors that were shown in the previous diagram, the perceptual, cognitive, and motor processors. It also includes a mention of serial and parallel processing. Some tasks can be done in parallel, while others have to be serial, or just one at a time. So parallel means they're happening at the same time. Serial means that one happens before another. So here's a breakdown of these three processors and what is entailed in each. So in the perceptual processor, we have all of our senses, including vision and hearing. For the cognitive processor, here we talk about long-term memory and short-term memory. And finally, we have our motor system, which executes the motor responses. So let's talk about each in turn. First, the perceptual system. This creates an internal representation of physical sensations. It stores temporary information in what's called buffers. That's why we say that there's an auditory image store and a visual image store. It's not the same kind of storage that we talk about in the cognitive system in terms of memory, or memory representations. It's really a very, very brief image store. Think of it like fleeting images. They're not long lasting, and it's like it's not like you've committed these to memory. Now, information in buffers can be transferred to working memory. The cycle time for the perceptual system is the time between when the stimulus is presented and when it's available in those buffers. And again, these buffers are very, very short term. They're very fleeting. When you get into the cognitive system, it connects inputs from the perceptual system to the outputs of the motor system. That's basically what the cognitive system does. So there's some interpretation here, right? And there's some coding involved here. You're thinking about things. So it handles learning, remembering, problem solving, and this includes working memory and long-term memory. Here the cycle time is longer when a greater effort is induced by the task or by the information. So obviously if you have a more complex problem, it takes longer for you to think about it and come to a conclusion. And usually what we tend to see is that cycle time shortens with practice. So the more and more that we practice, the better that we get at something, but also the faster that we get at something. This is key when we talk about how cognitive task analyses are constructed, because we include these different cycle times. This is why there are different times associated with these three systems. Okay. The motor system is where thought, or some sort of cognition is translated into physical or muscular actions. The motor system corrections require cycles of perceptual and cognitive systems. So the motor system will involve both perceptual and cognitive systems as feedback. These things happen in a loop. You do something, you see yourself do something, you think about how you executed that action, and then you adjust that action accordingly. And finally, the cycle time here is dependent on the type of action performed. So obviously some movements may take you a lot longer than other movements. So MHP, this is the Model Human Processor Subsystem and Interactions. So this involves an input and an output. Something goes in and you produce something from your thought processes, and it will delineate what kind of processing is involved. So in processing, there might be a serial action, like you press a key in response to a light, right? So you see the light first and then you respond to it. Or there might be parallel perception, like when you're driving and reading signs and listening to someone talk kind of all at the same time. That would be a parallel processing. Here's the model human processor with cycle times. A cognitive process generally takes around 7 milliseconds, but again, that's going to depend on the task. This is just an average. Perceptual processes take around 100 milliseconds, and motor processes take around another 100 milliseconds. So, once again, these are very rough estimates. It's really going to depend on the task, but these are some general guides or rules. So here's an example. The time it takes to enter a password at the unit level. So we have the task component on the left, the type of processor that we're going to be executing for that particular task, whether it be perceptual, motor, or cognitive, and of course we have our estimates of time, how long it's going to take that. So if you kind of go through all this, that would be you typing in your password. So you're locating the field for the password, you place the cursor in the field, you move your hands towards the keyboard, you have to think about or remember your username, you have to type your username, and so on and so forth, and each one of these has its associated processor. So as you can see, this is very much like a task analysis where you break down task components. As I mentioned, you do these things kind of in order here. That whole left column is very similar to a task analysis where the components are broken down, right? So note, however, that you don't really have a hierarchy here. You just kind of have this whole list of steps. Here, steps like recall username and recall password would not be included in a formal task analysis. In a formal HTA or traditional HTA. That's because they're not observable behaviors, they happen in your mind. Let's continue going through a few steps. When you're locating a field, you're perceiving information, right? So that's perceptual. When you place a cursor in a field, that's a motor response. You're moving your mouse over. Now when you recall your username, that's a cognitive response. So you give time estimates for each step in the far right corner, or the column, sorry. And all you need to do is give a rough estimate. These are based on, like I mentioned, the model human processor. And of course there are deviations. Maybe your keyboard is very small, or your username is very long, or your password is very long. These will all affect the overall time. But note that milliseconds is pretty short, right? So the overall time that we're talking about here is about 940 milliseconds or more. And that's probably because you're not taking into account the fact that there are strings of letters, not just one key. It's 950 milliseconds plus. This indicates that this is kind of the bare minimum of time that is required to complete the task. So if you do it as quickly, as efficiently, as correctly as you can, the best time that you can get is 940 milliseconds. Alright, the GOMS approach. GOMS stands for Goals, Operators, Methods, and Selection Rules. It's going to be very helpful for you to remember this acronym and what it stands for. Okay, GOMS, what it stands for. Make sure to remember it. Let's look at each in turn, right? Goals. So, what is the goal of the task? Operators. What tools can be used to achieve that goal? Methods. What are the alternative methods or ways of completing the task? Selection rules. How do I decide which method to use? Operator is tricky because people think of users as operators, right? And that's not wrong. But here with GOMS, we define operators as the tools that can be used to achieve the goal. So think about when we talked about devices. That's when we mean when we say operators. Okay. Let's go through an example. So goals. Our goal is to copy text from my term paper. The operator is the keyboard and the mouse. The method might be to use a mouse to select the text, or a mouse and then select one of the following methods. You go to the menu, do edit copy, click on the copy icon, or you do the hotkey Control C. Now your method might be different from the next person's, but that doesn't mean that you're right and they're wrong. They're just simply different ways of achieving the same goal. The selection rules are typically going to be based on previous experience. What have you had the most exposure to? What have you done previously to achieve this goal? Usually you'll draw on that, and if it was successful, you're more likely to remember that, right? So what has worked for you? You're probably just going to end up using what you used in the past. What you do is based on heuristics, and remember, oftentimes that means we're prone to biases as well. You might think that Control C is the fastest method, but when in fact it's actually selecting edit, copy, or something like that. Just as an example. I think usually the hotkey is the quickest. And there might be some other methods that are more effective, but because we're biased, we use the method that we're the most familiar with. Alright, the GOMS approach has 3 levels of granularity. GOMS model is a general approach to accomplishing a set of tasks. So that's the bigger picture. It's the general approach. It's the GOMS model to accomplish a set of tasks. Then it breaks down to the unit task level. So here you break users' tasks into what we call unit tasks, and then calculate estimates of the time it takes for users to perform those tasks. And finally, we can even break it down further. We can break things down to the keystroke level. Here we describe and predict the time it takes to perform a task by specifying the specific keystrokes needed. There's something particular about the GOMS approach. We'll get into that in a bit. So here's an example, or we've already seen this slide, right? So let's look at the slide again. The unit task level is very much like the cognitive task analysis. We have all of the task components, breakdowns, the processors, and the time estimates. That's the exact same thing as the cognitive task analysis. So this is how it's very similar to, this is how GOMS is very similar to the cognitive task analysis. The unit task level looks at procedural knowledge. So you have a series of if-then statements. So procedural knowledge is if-then statements. They're usually made up of that. So an example is, if the light is green, then press the green button. It allows you to make predictions like the time to perform a task, the number of errors you might encounter, and the learning rates. How quickly is someone going to be able to learn this? At the keystroke level, or the keystroke level model, you break the task down even further. Here you're breaking things down, like I mentioned, into keystrokes, and you actually specify what those keystrokes are. It might be a K, to press a key or a button, P, to point to a target on the display, and so on and so forth. And so these letters were kind of just, they represent the first letter in the phrase next to it. So key, it really kind of stands for key, right? Or sorry, K. K stands for key, or pressing the key or button. P, points to a target on the display. Home hands on input device. D is drawing a line segment. M is mentally preparing for the next action. And R we use for system response time. So R is response. The important thing to note here is that the keystroke operations are usually limited to computer and mouse tasks. Keystrokes cannot be conducted on other devices or systems. So that's one thing to keep in mind. So this is just an example of a key level model operation. This is everything broken down into the keystroke level. This table gives you an estimate of the operations that are defined in the KLM and the times associated with each of those. So here we even have the estimates based on ability. So we have the time for a poor typist, a good typist, and the best typist. If you're an excellent typist, it might take you 0.08 seconds, really quick. If you're a good typist, it might take you a little longer at 0.112 seconds, and so on. So all these times are for one single keystroke. Let's look at an example for replacing a word. If you're replacing a word, here is what the KLM model would look like. So reaching for the mouse, for example, would take you 0.4 seconds. And we have all the same columns as the cognitive task analysis, and we even have the total amount of time at the bottom. Right, so this is kind of summing up what the KLM model is. It's at the keystroke level. So why do we use the GOMS model? Well, it can predict the quality of existing systems or prototypes. You can check that the most frequent goals are achieved by relatively quick methods. It provides a quantitative evaluation of a technique, right? We get a lot of numbers from this. We can see objectively whether one design recommendation is faster than another design recommendation. So it provides that data so that we can choose the best design based off a couple choices, and we have that data as evidence to back that up, right? But of course, we have to be aware of the problems with GOMS. So it works pretty well for simple tasks, but boy, it starts getting really, really tough for larger tasks. Like all task analysis, it requires a lot of time, a lot of skill, a lot of effort, and with that, a lot of money. And finally, the results might be questioned by some. How someone may make the statement like, how useful really is all this data that you get? How useful is it to do all this work for an improvement of 1 second? Well, I mean, it's a valid question for sure, but one thing to keep in mind is that, let's say this is a telemarketing company, and they have 100 telemarketing phone operators working at any given time around the clock, 24 hours, and they're just calling people all day long. Well, if they save 1 second per person that they call, or 1 second per call, that's going to add up to a lot of money over time. So, the takeaway there is that these approaches are going to be useful in some situations, and in other situations they're not going to be very useful. Okay, so it's important to keep that in mind and to choose the most appropriate method. Alright, so let's finish with a summary. So task analysis in general describes behaviors at 3 levels: the goals, the tasks, and the actions. Tasks are usually viewed in terms of a hierarchical decomposition of tasks into subtasks. This is especially true with HTA. HTA and other related techniques focus on what actually happens rather than on what should happen. And depending on the goal of the task analysis, that might be a good thing or that might be a drawback. Cognitive task analysis techniques aim to describe some aspect of the cognitive characteristics of a user's tasks, such as loads on working and long-term memory, attention, making decisions, that sort of thing. That's really what distinguishes a cognitive task analysis from any other behavioral task analysis. Okay, so that sums up Lecture 7, Part 3 for this week. Alright, we'll see you guys next week.